Good morning, welcome back. Today we will discuss merging and splitting of Poisson processes. We started discussing merging in the previous lecture. We will just complete what we have to say and also do splitting today. Okay. So, for merging you have two Poisson processes. So, N1T which has rate lambda 1, okay. Sorry, rate, let us say call this lambda, and let us color this blue, and there is another process into T of rate mu, which is let us say a red process, okay. This is 0, okay. I am looking at the merged process, okay, and I am not able to distinguish colors. I am just looking at whether there is an arrival or not, okay. So, you see what I mean, there will be an arrival here, arrival here, arrival here, one here and so on, right. So, this is simply this process is simply N t is equal to N 1 t plus N 2 t, okay. So, this is a Poisson process of rate lambda, this is a N 2 is a Poisson process of rate lambda mu, and N 1 and N 2 are independent, okay. These two Poisson processes are assumed to be independent. Now, what we said in the last class is that the merged process N 1 t plus N 2 t is also a Poisson process of rate lambda plus mu, okay. So, this is the thing, if N 1 t is a Poisson process of rate lambda and N 2 t a Poisson process of rate mu, the process N t equal to N 1 t plus N 2 t is a Poisson process of rate lambda plus mu, okay. So, I forgot to say that N 1 and N 2 t are independent, okay. Please write that N 1 t and N 2 t are independent, okay. Otherwise this is not true, okay. So, we looked at this using this delta microslot picture, if you remember, right. So, you can look at some delta slot here, right. Let us say you look at some delta slot here, the same delta slot t comma t plus delta, right. So, here you can use definition 3, you can use, right. What is definition 3? The the probability of arrival in any microslot is lambda delta plus little o delta and IIP and SIP holds, right. So, you can have probability that, so N t equal to 0 is equal to the probability that, sorry, not N t, I beg your pardon. So, this is N tilde t comma t plus delta equal to 0 is equal to probability that N 1 tilde t comma t plus delta equal to 0 and N 2 tilde t comma t plus delta equal to 0, right. And this N 1 process and N 2 process are independent, right. So, this becomes a product, right. Yeah, correct. Now, this we know to be 1 minus lambda delta plus little o delta times 1 minus mu delta plus little o delta, right, which is equal to 1 minus lambda plus mu delta, then you will get lambda mu delta square, lambda delta little o delta, right, all that can be absorbed into another little o delta term. Similarly, you can write what is the probability that n tilde t t plus delta equal to 1. This is possible if there is one arrival in the first process and 0 arrival in the second process or the other way around, and they are independent of course, right. So, this will just turn out to be lambda delta plus little o delta times 1 minus mu delta plus little o delta. So, this corresponds to one arrival in the first process, no arrival in the second process, or you can have it the other way, right, and these are disjoint, right. You can have mu delta plus little o delta times 1 minus lambda delta plus little o delta, right. There is no other possibility. This if you simplify, so you will get something like, so you will get lambda plus mu delta, right. So, that corresponds to this lambda delta multiplying this 1 and this mu delta multiplying this 1, correct, and then you will get a whole bunch of delta square and little o delta terms, right, and delta. So, you essentially what remains is all 1 little o delta, and similarly you can argue that n tilde t t plus delta greater than or equal to 2, you can argue is equal to little o delta. Okay. So, we were so we have just gotten the right incremental distribution, we still have to prove SIP and IIP, correct. So, in particular I have to prove that the NT random variable has both IIP and SIP, right. So, to prove it is not difficult to argue at all. So, you take some interval, let us say you take some interval like that, right, and some other interval like that. You want to prove that in the merged process, you want to prove that the number of arrivals here is independent of the number of arrivals here, correct. So, the number of arrivals here is nothing but the sum of arrivals in the corresponding interval in the two processes, right. Now, for the first process of course IIP holds. So, in the corresponding interval if you look at it here, right, you can, this is not at all difficult to argue as you can imagine, right. So, you look at the corresponding intervals here, right, and this process satisfies IIP. So, this is independent of that number of arrivals here is independent of number of arrivals here, and of course, number of arrivals here is independent of number of arrivals here. Why? Right, the number of arrivals in that interval is independent of the number of arrivals in that interval. Why? Because the processes are independent. Okay. So, using IIP for the individual processes and the fact that the processes are independent, you can get IIP for the composite process or the merged process. Okay. Now, you have to argue SIP, sorry, maybe this should be here. Should be here, right. So, for SIP what do you do? So, you have to prove that number of arrivals in any interval is only a function of the width of the interval, correct. But the total number of arrivals in this width is nothing but the total number of arrivals in the two processes put together, right, and for that SIP holds, right, for the separate processes. From this you can argue SIP for the merged process. Okay. So, I will just say IIP and SIP follow from the respective properties of N1T and N2T and the fact that they are independent. Okay. Now, this is I mean I happen to use definition 3, right. It turned out to be quite natural in the sense that I am just looking at the increments of the merged process. Now you can also look at other definitions, definition 2 or definition 1, all right. For example, if you want to do the second definition, right, using definition 2, right, proof using definition 2. What is definition 2 by the way? Sorry, definition 2 says that NT is Poisson PMF for every t. NT is Poisson with parameter lambda t, right, or whatever the or mu t, whatever the parameter is. Now, and of course SIP and IIP, right. See that SIP and IIP hold I have already shown, just I mean using the previous argument still holds, right. I just have to prove that. So, if I look at this, probably it is n of t, which is so if I just look at t equal to n, right. This if this turns out to be Poisson with Poisson PMF with parameter lambda plus mu times t, then I am done, right. So, this is nothing but the probability that so I want the PMF. So, for any t I want the PMF of n1 t plus n2 t, correct. So, what is this is the question, but I already know that we know this. What is the PMF of n1? It is e to the minus lambda t to the k by k factorial for k equal to 0, 1, 2 dot dot dot. And similarly, this also I know, this is mu t power m, so on, right. So, I know that n1 is Poisson with parameter lambda t, n2 is Poisson with parameter mu t, correct, and I want to find the PMF of n1 plus n2, right, and this n1 t and n2 t are of course independent, right. So, you are looking at sum of two independent Poisson random variables, right, and you may already know this, that the sum of two independent Poisson random variables with parameter let us say lambda 1 and lambda 2 is Poisson with parameter lambda 1 plus lambda 2, right. So, we can either use, so how do you prove that? Yeah, you can use a discrete convolution, right. So, we can use discrete convolution. You see you are allowed to use convolution because n1 and n2 are independent, right, otherwise you cannot use convolution. You can use discrete convolution to show that this is also Poisson with parameter e power minus lambda plus mu, okay. Lambda t plus mu t whole to the n over n factorial, correct. You know how to convolve, right, you can do convolution. But so if you were doing undergraduate probability course, you will probably sit and do the convolution. Now we already know something about Poisson process, so we can, there is actually a cleverer way to do this, okay. See, you just consider one Poisson process, okay. If you have one Poisson process, you look at intervals 0 to t1 let us say, and intervals in another interval t1 to t2, t1 all right, sorry 0 to t1. So, let us, this is a separate consideration, okay. just to see that sum of two independent Poissons is a Poisson. So, they say this is 0, let us say T 1 and this is T 2. So, this is T 1 plus T 2, okay, and you have some Poisson process running, all right. So, you know that this the number of arrivals in 0 to T 1 is Poisson distributed with parameter what lambda T 1, correct, and the number of arrivals in this T 2 T 1 to T 1 plus T 2 is Poisson with parameter lambda T 2. Why? SIP, right, because the width is T 2, and of course, the number of arrivals in this width in 0 to T 1 is independent of the number of arrivals in T 1 to T 1 plus T 2, right, and so these two are independent, right. Correct. Now, the total number of arrivals in this entire width, if you look at right this width is, we know this to be Poisson with parameter lambda T 1 plus lambda T 2, that also we know, right. So, what have we established? So, I know that sum of two Poissons with parameters lambda T 1 and lambda T 2 independent Poissons is a Poisson with parameter lambda T 1 plus lambda T 2, the parameters are getting added up. See, that is all that I want, right. In the other case, when I am merging two processes, again the parameters are getting added up, the only difference there is that the rates are different, the T is the same. Here the parameter lambda is the same and the T's are different, but it does not matter, right, you are just looking at two Poisson PMFs, this has nothing to do with stochastic processes, right. So, call lambda T 1 to be xi 1 and lambda T 2 to be xi 2, you are getting a Poisson PMF with parameters xi 1 plus xi 2, and that is all that is happening even in the merging case, right. So, this is just a cleverer way of showing that sum of two independent Poissons is a Poisson with the parameters added up, okay. Is this argument clear? So, you do not have to, if you are bored of convolution, you do not have to convolve, okay. I mean this is a clever way to see this, okay. So, this is also a nice proof, and of course, IIP and SIP are, we already did, right, you have to show IIP SIP also. So, definition 2 also is a valid way to approach this result. Do you know how to approach this using the first definition? So, proof from definition 1. Definition 1 is what? Independent exponential interarrival times, right. So, just again let us look at the blue process and the red process. See, I am doing this so that I may not do this for the splitting case, for example, I will not do the proof using all three definitions, okay. I am just doing this once so that you get the hang of it, okay. So, this is your blue process and that is your red process. Okay. So, let me call, so I want to call this guy as x1, x2 etcetera, okay, and let us say I call this guy y1, y2 etcetera, all right. Of course, merge process will have arrivals from both, right. Now here if you look at the first interarrival time, let us say call this Z1, Z2 etcetera. What is Z1 in terms of x1 and the x's and y's? Yeah. So, the first arrival in the merged process will simply be at, correct. Now, x1 is exponential with parameter lambda, y1 is exponential with parameter mu, right, that is what I am given, and of course x1 and y1 are independent. Now, you probably know this already, but you can also derive it from first principles, it is not at all difficult, that the minimum of two independent exponential random variables is
product of complementary series.
Yeah, he is right. What he is saying is that the complementary CDF of the minimum is the product of the two complementary CDFs. So, essentially you will get that Z1 is also exponential with parameter lambda plus mu, okay. So, if you look at this Z1 greater than t, right, this is equal to the probability that x1 greater than t and y1 greater than t, right, because the minimum is greater than t, then both are bigger than t, correct, yeah. So, this is of course equal to the product, sorry, y1 greater than t because of independence, the two processes are independent. So, x1 and y1 are independent, right, and this is nothing but e power minus lambda t times e power minus mu t, which is e power minus lambda plus mu t. This means that Z1 is exponential with parameter lambda plus mu, correct. Yeah. So, what have we proven? So, we proved that in the merge process the first arrival time is exponential with parameter lambda plus mu, which is correct, which is what you want, right. Are we done? Now, we have to prove that the subsequent interarrival times are also independent and that they are all independent. So, they are all exponential and they are all independent, right, correct. This basically follows from memorylessness, okay. So, it is so the way I have drawn it, this blue process has created the first arrival, of course it could also be that the red process created the first arrival, but nevertheless see your the first process created an arrival here, let us say at some particular time, right, this is let us say some time tau, right. For the red process from the time tau to the next arrival is what? Is also exponential, we proved the theorem, remember, you fixed a time t and that you looked at the time to the next subsequent arrival. So, you look at the first process, the second process does not know anything about the first process, it is just some time tau. At the time tau, the time to the subsequent arrival of the second process is an exponential with parameter is an exponential with parameter mu, right, the rate of mu tau, it is an exponential parameter mu, that is all that I am saying, right. And of course, the next arrival in the blue process is of course an exponential with parameter lambda, right, by definition. Now, so the next arrival in the composite process is the minimum of this guy and the x2, right. This time to the next arrival in the red process is exponential with parameter mu from the theorem that we proved, and this is exponential with parameter lambda, correct, and these two are independent. Why? Processes are independent, right. So, again you are looking at minimum of two independent exponentials, right. So, then you can argue, so using memorylessness that subsequent inter arrival times in the merged process also independent exponentials with parameter lambda plus mu. So, the trick is, so you have gotten the first arrival in the merged process, right. In this picture it come from the blue process, you look at the time tau, okay. The time to the subsequent arrival in the red process, this guy is exponential with parameter mu. We know this from the theorem, right, and it is of course independent of everything that happened in the past, and likewise this is also an exponential, right, the time to next arrival here. So, the time to next arrival in the merged process is a minimum of 2 exponentials which are independent, because the 2 processes are independent, right, clear. So, again it will be an exponential with parameter lambda plus mu, okay. And to show that this so the then this should be independent of the previous exponential, right, that follows from again the theorem that said that this with this exponential is independent of everything that happened in the past, right, and of course this exponential is also independent of everything that happened in the past, right. So, these two together you can get what you want, okay. So, what have we shown? So, we have shown the same result in 3 different ways, they are using the 3 different equivalent definitions, which is not surprising, right. I think all 3 are insightful. Perhaps the most intuitively easy is the first one, right, you look at these micro slots and you get this straight away. For the definition 2 and definition 3, you have to know something about the sum of Poissons being Poisson or minimum of exponentials being exponential, right. So, that, but there is no approximation involved. So, in the definition 2 proof and the definition 1 proof, but there is no approximation involved, that is the nice thing, right, it is exact, but you have to argue somewhat carefully that these bits are independent of the past and all that. So, completing the proof requires some writing down a bunch of arguments, right. This what I have said in this one sentence, you need to write it out properly in terms of the theorem, that big theorem we proved, the memorylessness theorem that we proved, right. Good. So, this concludes the module on merging.